Hey Homo sapiens, Parman here, and welcome to the very first episode of Parse This Paper with Parman. In this series, I'll pick an interesting research paper, give some background info on the information in it, and then go through the paper itself in simpler terms. Today, we'll be looking at a paper titled A Senescence-Centric View of Aging, Implications for Longevity and Disease by M. Borgeson, W. M. H. Hugars, M. Varela Aaron, N. Talma, and M. DeMaria. I'm sorry if I mispronounced any of those. And as you might have guessed from the video title, we'll be going in depth about human longevity. But before we even dig in, what is human longevity? Researchers in this field are working towards increasing our health span. And what's health span? Well, you've heard of lifespan before, right? It's the amount of time you live on average. But as you might have sadly noticed, the last few years of life are often riddled with disease, illnesses, and a low quality of life in general. So, researchers in longevity are aiming to increase the amount of time we're healthy, our health span, rather than just alive. Pretty cool, I know. Now, there are multiple different things that scientists think lead to aging. They're called the hallmarks of aging, and there are 9 of them, including genomic instability, telomere attrition, epigenetic alterations, loss of proteostasis, deregulated nutrient sensing, mitochondrial dysfunction, cellular senescence, stem cell exhaustion, and altered intercellular communication. Don't worry about the fancy words, we'll dig into a few of them that are pertinent to the paper. But 1 second before we actually go, let's define what aging is in a scientific sense. Aging is the buildup of damage on a molecular and cellular level that slowly results in diminished mental and physical abilities. Now, let's dig into some hallmarks. First off, let's talk telomere attrition. Telomeres are like little caps at the end of your chromosomes, your bundled up DNA, that are insignificant copies of genes. The exact sequence that's repeating for those random fact lovers is TTAGGG. Telomeres aren't actually expressing anything important, and so when your DNA is copied and some of it's lost, it's not a big deal. Whenever you're undergoing the cell cycle, the cycle during which your cells proliferate or multiply, the telomeres have got you covered. Another way to think about it is like shoelaces. Imagine your chromosomes as the shoelaces. Telomeres are like those little plastic caps at the end of the laces that protects it from getting frayed or ruined. But, and this is a big but, telomeres don't regenerate, at least not in humans, and at least not yet. So as we grow older and our cells divide again and again, our telomeres shorten. In fact, during each division, we lose anywhere from 25 to 200 base pairs. That means that eventually, our telomeres will completely run out. That's when the cell faces something called cell cycle arrest. The body tells it to stop dividing to prevent dysfunctional DNA and diseases. This is where we reach a crossroads of sorts with definitions. This cell cycle arrest can either be reversible and temporary or permanent. It's permanent when the cell isn't getting any growth factors. The cell becomes known as quiescent. It has low metabolism, protein synthesis, and cellular functions, and no cellular size growth. However, when the arrest is permanent, it's, wait for it, called a senescent cell. Pretty smooth segue, I know. I don't want to confuse you too much just yet, so we'll go with a simplified definition. Senescence happens when there are 2 things present. Number 1 is growth factors, which, you guessed it, promote the growth of the cell in the continuum of the cell cycle. Number 2 are CDK inhibitors, which block but not fully stop the cell cycle. Just a little extra negative info, a CDK is short for a cyclin-dependent kinase, which promotes the cell cycle, and so CDK inhibitors block it. A paper titled Cell Cycle Arrest is Not Senescence by Mikhail V. Blagasklony uses the absolute perfect analogy to differentiate between these 2 fairly confusing terms. For quiescent cells, it's like you're driving a car and you're pressing on the gas pedal to accelerate. Then you lift your foot off and you decelerate. That's when you have no growth factors. If you press on the gas pedal again, boom, off you go. That's when you're getting growth factors again. For senescent cells, however, The CDK inhibitors act like brakes, while the growth factors act like a gas pedal. It's like you're pulling the brakes and pressing on the gas pedal at the same time. That can cause irreversible damage. But wait, why is senescence even bad? Senescent cells aren't really benefiting the body, though they do have some benefits, and I'll leave some links down below in the description box for you to check those out. But this quote from the original article sums up the damage they can cause perfectly. Accumulation of senescent cells during aging fosters inflammatory responses, alters cell-to-cell communication, and reduces regeneration, thus leading to tissue dysfunction, frailty, and disability. And there you go, a fairly quick backgrounder before we dive in brain first into the paper. There's so much more to explore just within the hallmarks of aging. So let me know if you want videos on them down below in the comments. If you want to watch a video about stem cells, the amazing cells within our body that can self-replicate and differentiate into more specific cell types, make sure to click on the eye right over there to watch it. First, let's talk about Alzheimer's disease, or AD, a disease that 1 in 10 of us watching this right now will have after age 65. Well, in the astrocytes of AD patients, an overexpression of P16 has been noted. Alright, let's unload that gibberish. You can think of astrocytes as cells essential to the central nervous system. And P16, those are just CDK inhibitors. Remember them from before? And it's not just in humans either. In mouse models that have plaques related to AD, there's been an increase in P16 levels. Up next is type 1 diabetes. I'll keep this one super brief. In a study, removing senescent pancreatic beta cells was actually able to protect from type 1 diabetes development. Last one up is chronic kidney disease, or CKD for short. Based on some research done on human and mouse models, senescent tubular kidney cells may actually lead to CKD. Tubular kidney cells are just those found in the renal tubules, and the tubules are just highways for removing waste and other fluids from your blood. What's more, our best friend P16 may actually play a role in CKD too. Based on some research done on mouse models to improve some hallmarks of the disease, removing cells expressing P16 has actually been useful. Now, this wouldn't be a very special first episode if there wasn't something a little extra. There are so many promising advancements in the longevity field, but I want to highlight one company specifically. Yep, it's time for a company spotlight on Unity Biotechnologies, co-founded in 2011 by Nathaniel David, Jan van Dersen, Judith Campisi, and Daohong Zhu. Backed by Jeff Bezos, the company's focus is on senescent cells and removing or modulating them to help increase the human health span. Recently they were working on a candidate drug called UBX0101 to help with osteoarthritis. They were actually in a phase 2 clinical study, but after seeing no significant results, they shut it down. That does not mean there isn't good news too. They have just dosed their very first patient with a new drug called UBX1325 in October 2020. This time the drug is focusing on ophthalmology. The current president, Nathaniel David, has co-founded 4 other biotech companies that have together raised over $1.5 billion in financing. And he was named one of the top 100 innovators under 35 by the MIT Tech Review. And that brings us to the very end of this video. If there's just one thing that you take away, let it be that we need to increase our health span and not just our lifespan. Oh, and of course remember that an overexpression of P16, the CDK inhibitor, is real bad. Thanks so much for watching, and I'll see you next time. Bye!